Hi, everybody. Thank you for being here. It's a pleasure to have the opportunity to tell you about what has happened in the past 10 years in gravitational wave astronomy. It is a complete coincidence. We did not coordinate that Hector would mention the press announcement 10 years ago on February 11th, 2016, and I'm about to start my lecture with that day exactly. So for my talk, I'm gonna give you a little bit of how the field started. It's really, we opened, I'm not supposed to use laser. So how the field opened up 10 years ago, gravitational wave astronomy. And it had a long history. We were trying, many people, hundreds of people were trying for over 40 years to get this to happen. And many people did not believe that it would happen. So I'm going to start with a little bit of history. Then I'm going to focus on parts of what we're doing right now. I will highlight some work from my group and from the collaboration. And then if there is a little bit of time, I will transition and highlight some group from the Astro AI Institute that affects how we're doing the modeling of the gravitational wave sources that we're seeing. So we'll see how the time goes, okay? All right, so 10 years ago, February 11th, 2016, a day that we'll never forget, the ones who were part of this collaboration. Dave Reitze, the director of the LIGO lab at the time, still the LIGO lab director, actually, and a Northwestern graduate. Gabby Gonzalez, our spokesperson at the time. Ray Weiss, the father of the field, along with Kip Thorne, whom you may have heard his name. Ray, unfortunately, passed away just a few months ago, and last week I was at his memorial conference and family memorial. So we all remembered his amazing contributions and unique. And in fact, we are all saying there is no Ray Weiss. He cannot be replaced. So Dave stood up.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Now, I know I have to keep time, but I also have to tell you that this was not the plan for Dave. So I was in the room, there were rehearsals of the press conference the night before, the morning of, an hour before the press conference started, and they were all going horribly bad. And because they had elaborate little story of how to do it, et cetera. And then Dave at some point said, well, that's it. I'm just going to stand up and say what we did. And this is what he said. And it has stayed as a mic drop moment for our collaboration. OK, so what is it that we detected, that first detection? It's basically two black holes. We're going to talk about what black holes are. One orbiting around the other, and emitting gravitational waves. We're going to talk about what gravitational waves are. And as they emit gravitational waves, they're losing energy from their orbit, from their motion. So they're coming closer and closer together because of this lost energy until they merge into a single black hole. That single black hole is a little disturbed, but emits a little bit of more gravitational waves, but then it settles in a nice spherical, quiet black hole, and there is no more gravitational waves coming. So it's a catastrophic event that doesn't continue, okay? It's a transient event, we say. It happens, and then it stops. And the kind of signal we received has this kind of waveform. It's a wave, an oscillation, and it comes to an end, but it peaks right when the two black holes are coming together and touching. And what you may see is that the peaks in this simulation, the peaks of the waves and the troughs are coming closer and closer together. That means the frequency of the wave is increasing. And also the height of every oscillation is also increasing. So the amplitude, the strength of the wave is increasing as well. So before I tell you more about the signal, just to make sure everybody is on the same page, where do these LIGO is the observatory we use for the detection, where do these LIGO black holes come from? They're basically corpses. They are the most compact corpses that are formed at the end of the life of stars. Not stars like our sun, but a lot more massive, most typically more massive than 20 times the mass of our sun. And when these stars completely exhaust the fuel in their center, then they cannot sustain themselves in their size, and they end up collapsing. And sometimes they collapse, the whole star collapses and forms a black hole, okay? So that's all we need to know about black holes for today's lecture. Also, we call them compact objects, and they're truly compact. They're compact, comparable to human scales. So a black hole of 3 times the sun, or 3 times the mass of the sun, has a radius. Now, it's not a real radius, but it is sort of an imaginary radius that has physical significance in how these collisions happen. The radius of that, let's say, radius surface is 9 kilometers. It's comparable to the size of Manhattan. Okay, so now you have a star that may be 20 times the mass of the sun collapsing into something that's 10 kilometers, 20 kilometers across. The surface, by the way, is the surface where if anything crosses through the surface, it never can come out. It's the surface where if you wanted to escape the gravity of the black hole, you need to have the speed of light. Okay? So that's our definition of black holes for today. And the way we detected these waves is with a new kind of telescope. It's not exactly a telescope. It doesn't look like a telescope. It doesn't smell like a telescope. And it is, often we call it a detector. And it has this L-shape configuration. And we have 2 detectors in the US, one in Louisiana and one in Washington State. And the shape is an L shape for particular reasons that I will come back to, but it has a corner station and then 2 arms at right angle, and the arms are 4 kilometers long. We would have liked them to be longer, but that's what we could build at the time. Now, construction of these started in 1992-3. Construction finished in 2001, and the detector started collecting data in 2002. The detection happened in 2015. And what was happening for all those years, it's not that we were sitting waiting for the signal to come, but the initial detectors were not sensitive enough. And the data analysis methods were not sophisticated enough. So for 13 years, people were working on making these detectors more and more sensitive. The binary black hole collisions that eventually we detected don't happen often. They don't happen in our neighborhood regularly. So you need to be able to detect them at large distances because they are so rare. But to detect them at large distances, you need to have a very sensitive machine. Okay? So improving the sensitivity took quite a bit of time. Also, the the problem with the sensitivity has to do with the fact that the gravitational waves, these little scribbles or the oscillations you saw, are actually minuscule. They change, and they're oscillations of space-time. I'll tell you about that too. Just be patient. They're oscillations of space-time, and they're changing, forget time. They're changing space when they travel by 1 part in 10 to the 21. Doesn't mean anything to you. So, but 1 part in 10 to the 21 is a really, really, really small change in the space. So how do you measure something so small? Ultimately, the measurement happened, and now it happens routinely. And it was 10 years ago, and it still is the most precise measurement ever made by humans across all of science and engineering. So from an engineering perspective, and the engineering happened because of amazing science that preceded it, is almost a miracle. It's not a miracle. Humans made it. But a lot of people doubted it. In fact, Ray Wise had the idea for this configuration, doing it this way, and for decades, he was made fun of. Serious scientists and engineers thought he was a crackpot. Not quite a crackpot, but he was made fun of. And when I joined as a postdoc, and I was the first, as Ray said, card-carrying astrophysicist to join the collaboration, my astronomy mentors told me, you will destroy your career. All right, now let's take a step back. Okay, what is space-time oscillations, gravitational waves? Well, it has to do with the understanding connected to Einstein's theory of general relativity. So gravity, before Einstein, was understood based on Newton's theory. And Newton's theory, we can describe it in many different ways, but for our purposes, we're going to focus on the fact that the understanding was if you have two masses at some distance, then they know about the existence of each other instantaneous. And it's like a rod connects them. And if you kick one of them, then it's going to move around the other as if they are connected with a physical rod. And space around it is unaffected. Nothing happens. Distances don't change between reference points. Einstein comes, and for a number of reasons, this didn't come out of the blue one morning having his coffee, but it was a brand new idea that mass, actually, just existence of mass affects space-time. And if we think space, forget time. We're not going to talk about time. It's a little too much. Plus, I don't want you to be paying attention to time. To the clock. So mass, by its existence, curves space. So if space were two-dimensional instead of three-dimensional around us, then it would be curved and bended and warped, and reference points in the presence of mass, the distance would change. Now, if I give a kick to one of them, then the motion of the mass is just a response to the geometry, the curvature of the space. And it starts moving because of the curvature, and it acts like an egg beater in a way, and it now generates waves the same way an egg beater starts generating waves in a liquid, okay? And ripples. So gravitational waves are now oscillations of space-time, and they get generated by masses that accelerate at any strength of acceleration They get generated around these masses, and they can propagate through the universe at the speed of light, and they carry energy. Waves carry energy. That oscillation, whether it's electromagnetic fields or the space-time, the wave as it travels carry energy. So it carries energy from what? From the motion of this pair. And if it's two black holes, then the pair of black holes is going to in spiral closer and closer together, and they have nowhere to go other than collide. Okay? All right. Now, if you want to detect something new, you have to think about what is it that it does in your surroundings. And then what kind of detector can measure or detect or interact with that effect. So the effect of gravitational waves is oscillatory disturbances of space-time. So if you think of a circle of points on the plane of the screen, and there is no gravitational wave, then they are sitting in a circle unaffected. If a gravitational wave is traveling perpendicular to this plane, then the points start oscillating because space is oscillating. And they oscillate in two different ways, one in a cross-like shape, and simultaneously they're being stretched and squeezed in an X kind of way. We call these that they have two polarizations at 45 degrees. And a wave is basically propagating because it's not just the plane of the sky, but it's the, of the screen, but it's also the plane before and before and before and the plane after. So now you have propagation of the wave, and the reference points are moving this way, okay? Now, the oscillation is up, down, up, and squeeze, squeeze, and stretch. And these things are going together, okay? The L shape of the detectors is there to measure this simultaneous squeeze, stretch. And the fractional change of the wave, how much the distance between two undisturbed points is changing is proportional to what we call the gravitational wave strain, which is the amplitude of the oscillation, the amplitude of the wave. Now, these waves are extremely weak. That 1 part in 10 to the 21 is the equivalent of having the whole Earth, a wave is going through, and the size of the Earth is oscillating by 1 proton. And you want to measure this. Now, do you understand why people thought Ray Weiss was crazy? Okay. That was the goal. What was the proposal? Laser interferometry, with very complicated optics that I'm not going to go into discussing, but laser interferometry doing an interferometry measurement that allows you to do precise distance measurements. In fact, the truth is it is not distance measurements that we're making. It's actually time measurements that we're making. But it's easier to think about distance differences. So how does this work? Well, we have the corner station of the telescope. And at the corner station, a lot of optics exist, but the fundamental thing that happens is that a laser gets shot out from the source and goes down the 2 arms of the telescope. It bounces off at the end. It bounces off very special mirrors that are suspended so they are as free as possible. They come back, and they get guided by optics to come and interfere, now, the two lasers. And the whole thing is set up so that if there is no gravitational wave passing through, they cancel one another, the two lasers coming back. So if you add up these two waves here, they're going to give you 0. If, however, you do have a gravitational wave coming, then what will happen is the end mirrors are going to start doing this squeeze, stretch, squeeze, stretch, squeeze, stretch. And when the two waves come back, they're going to combine, but sometimes they will give you dark current, 0, they will cancel out, and sometimes they will be bright. And it is that change that we're measuring. And that's the amplitude of the wave that we can measure very precisely. Okay? So that's how interferometers in Louisiana and Washington were working. And eventually they were working with high sensitivity enough to detect the first binary black hole. A few years later, a third interferometer was added from the Europeans, and it sits in Pisa, Italy. And they act as, you may have come across this analogy, we talk about gravitational waves as sounds. We convert them into sounds. There is a coincidence that the frequencies LIGO operates in and can be sensitive to are the same frequencies in sound waves that our ear is sensitive to. That's coincidence. The real reason gravitational wave telescopes are like ears is because they are like ears, human ears. So telescopes, normally electromagnetic telescopes, are like eyes. They have to point. Our eyes, I have to point to look at you, but I cannot see the people behind me. Ears can hear from all over, right? Maybe I can hear better if I point my ear, but we can hear sounds from all over. Gravitational wave detectors can receive and detect gravitational waves from all directions. So they are ear-like detectors, not eye-like detectors. So we're listening to the universe. Now, again, a sense of how sensitive a measurement this is. The gravitational wave strain, 10 to the minus 21, is the delta x over x. On the size of these detectors, 4-kilometer arms, the delta x is 10 to the minus 18 meters. And that is 1,000 times smaller than the size of a typical nucleus. Okay, it's unthinkable. All right, so this was our first detection. And it was stunning that we could actually see it by eye. And most detections we cannot see by eye. We could see the data in the two detectors going up and down at first noise, but going up and down and clear more, stronger, up and down. And the peaks are coming closer together, and then it dies down back into noise. Another representation, frequency as a function of time. At first, nothing. And then the frequency is increasing. We call these bananas. And the light, the color, becomes brighter because the amplitude is increasing. The amplitude is increasing. The frequency is increasing because they're going like crazy as they come closer and closer. The speed is higher and higher, just like a skater when they close their arms. They go faster and faster. So the frequency is higher. The amplitude is higher because actually the turmoil of the space-time is much stronger. The masses are closer and closer together, and they're moving at higher and higher velocities. For this one, a collision, the final velocities before collision was half the speed of light, 60% of the speed of light. So this fast motion and acceleration disturbs the space-time really strongly. You get high amplitude, okay? All right, so this particular merger was two black holes, and we could measure 30 times the mass of the sun, each black hole. We could measure the distance, about 1 billion light years away. This wave was traveling for 1 billion years before it hit our detectors that September. The wave carries energy, as I told you, enormous energy in gravitational waves, not in light. 3 million times the energy that you need to destroy the sun. And if that energy was light, then for that fraction of a second, it would have been 50 times brighter than all the stars in the universe. Not the stars we can see, all the stars in the universe. So this detection, the year later, was selected or announced as the breakthrough of the year across all of science and engineering. And our sort of fathers of the field also were awarded the Nobel Prize. And the whole collaboration is proud. So Ray Weiss, Kip Thorne, I've already pointed them out, and Barry Barish, who was instrumental in putting together and organizing this collaboration in the lab, getting us to work effectively as a collaboration of hundreds of people achieving eventually what we needed to achieve. Now we'll come to the present. 10 years later, we have detected 202 gravitational wave mergers, okay? Because one detection was thrilling, was life-changing, opens a new field, but it's not astronomy. What do we know about the universe if we only know our sun? What do we know if we only know one galaxy? Not much. Now we're building a population of these mergers. And I won't talk about other types of mergers other than black holes. The majority of mergers are the blue triplets, one black hole, second black hole, merging and forming a third black hole. But we have also detected other compact objects that it's not the topic of our discussion today, but we call them neutron stars. They are of lower mass. So this is how massive are the black holes. And down here we have something called neutron stars, less compact than black holes. The other colors are black holes that were detected through different means in electromagnetic waves and through indirect means, and then neutron stars that also were detected through electromagnetic waves, okay? So now the population of black holes has increased. By the way, 220 gravitational wave mergers, so times 3 individual black holes. So now we're asking population questions. I'm going to skip the math. You can ask me, how do you go from that little scribble up and down, frequency, and you can now say, the source is that far away, and the masses are X times the mass of the sun. And we can also measure how fast they're spinning. But there's math behind this business. So now that we're studying black holes as a whole population, we're asking questions we could never have asked before. We're trying to understand, how do these pairs of black holes actually form? We had never seen pairs of black holes. We had seen black holes in pairs with other stars, regular stars. But we had never seen pairs of black holes. We had predicted them, and we had predicted them as forming primarily through pairs of stars. So most stars, unlike our sun, live their lives in pairs. They get formed, and they have a partner in orbit around one another. If they are massive stars, then if they survive life together with interactions and non-interactions, then they'll end up, and they stay together through their life, they will end up becoming a binary black hole. That's, I hope this is not my phone. OK. So we call this formation of binary black holes through isolated binary evolution. So the two stars, they just interact with one another, nothing else. But there are other ways to form black holes. You can form black holes in dense environments. Single stars form individual black holes, but they find themselves in extremely dense regions, not the kinds of regions we live in, where you can have millions of stars in a tiny, tiny space where they cannot avoid one another. And they form pairs because they're kind of dancing too close to one another. Okay? So two fundamental ways of forming. The question is, the ones we really see in the universe, this is all theoretical. The ones we see now in data, how are they forming? OK, so how do we answer these questions? Well, the first most fundamental thing we measure through the mergers is masses. So first come the masses. And now we're not looking at one mass here, one mass there. We do a whole statistical analysis. We take into account the fact that our detector does not see with equal probability all types of masses. So we correct for effects. And we analyze now the population characteristics, not individual sources. So one question that has been relevant for 97, oh my goodness, 20 years, 30 years. I can't even subtract. My brain does not want to absorb it. One question that has persisted has to do with low mass black holes. A different type of population in electromagnetic astronomy has indicated that low mass black holes don't exist. I will not go into many details. I'll try to stick to the main points. That for some reason, black holes between 3 and 5 times the mass of the sun don't form. Stars avoid them. Why? We don't know. That was sort of the wisdom for a while, for decades. So the question was, before even in anticipation of detections, will gravitational waves find them? Because it's a completely different way of detecting them. And basically, there was a hint, depending on how you model the population, maybe there was a hint that we are seeing a valley. But if you model the data in a different way, the uncertainties were high, and maybe there's no valley. It's all flat. Well, the answer came clear when we detected, I'll skip this, a single source. Our sources have very fancy names. They're called GW, gravitational wave, and the date we detected them. So we discovered this system, and one of the components had a mass dead inside the center. And even though it was a single source, even by itself showed that here's a black hole right dead in the center of the gap. But even if you did statistical analysis, and then you asked yourself, now if I incorporate this one source in the population, I can calculate in the same way we did it with X-rays, I can calculate what is the minimum black hole mass of the population statistically, you find that the minimum is 3 to 3.5, not 5, which is what we find when we do the same analysis with the X-ray black holes, where we were finding 5 or 4.5. This analysis, by the way, I'm showing Will Farr's cute face. He was my postdoc ages ago, and now he's a researcher part-time here at the Center for Computational Astrophysics at the Foundation. So that question has been settled thanks to gravitational waves. Now you might say, well, what about the X-rays? We still don't see them. Nobody doubts that. Ages ago, a collaborator of mine and myself had hypothesized that not seeing them in X-rays was actually a selection effect. And we have now argued that there is a way to explain that gap, but it's not a true gap in nature. All right, how am I? Okay. Another topic of present attention. You look, a lot of things in astrophysics, you look at populations and you find power laws. So in log plots, this is not log plot, you find straight lines of different properties of populations of things. Stars, planets, galaxies, and properties of all of these things. Now that we have tons of masses, 600 and plus masses, we put them together, and it's not a power law. It has peaks, clear peaks, strong peaks, and it has a bump. And honestly, it has some other things and something else that look like jokes right now, but when we had fewer data, this peak and this bump also looked like jokes. So we'll see what we find in the future. Let's focus on the clear peaks and bump. The question is, how are these formed? And what are they telling us? We don't know enough about black holes. And are they associated with one or the other formation mechanism? These are all questions we had no way of asking before. So these features are real. We have analyzed the data in many different ways for the experts with parametric and non-parametric ways, et cetera. The peak at 10 solar masses, the bump at 35 solar masses is there. No one doubts that. So how can we figure out what this is? Well, I'll go directly to the answer. What we're finding now is that this very sharp peak at 10 solar masses, recent work with a past graduate student of mine, now a junior fellow at Harvard, is showing us that it's directly connected. You can change anything you want in evolution of isolated binaries. But the only thing that affects the presence of the peak, it's always there, but the location and the width, it's changing only if you change, don't mind all of these names, if you change the mechanism, the details of the mechanism of how stars go from stars to black holes at the very end of their lifetime. And that we don't know. We don't understand it. We can't simulate it. So we have recipes. And if you change that recipe, you get the peak to go at places where the data doesn't have a peak. Or you get the peak to be very broad. So we're going to be using the peak in the data to learn more about the connection between the star progenitor and the black hole that is forming. I talked about isolated binary evolution, but actually you can get a peak. This is now a logarithmic scale, so it drops very, very fast. So there is a real peak at 10 solar masses, even with the dense stellar environments, the second path of forming. Because at the end, it has to do with star-forming black hole, not with what happens later. So could it be that it's not just binary evolution? So the answer, I'm sorry, not just binary evolution isolated. So then you realize we cannot just be looking at masses. And that's the beauty of all the information we can extract from gravitational wave observations. If you just look at masses, the answer is sure, it could come from any of the two channels. If you look at mass ratios, so the ratio of the masses of the two black holes, the pairing mechanism, and if you look at a quantity that tells you something about the spin of the black holes, this was in the math slide I skipped. I will not give you the details now, but basically what you see is that the data are the ugly, because we don't have yet enough data. The data give you a clear peak between 0.6 and 0.8 in mass ratio. The blue is the data. For the connoisseurs, the black dashed lines are the priors on the distribution. So the data are clearly off the priors. We have a real measurement. The red lines is what you get from binary black holes that form in dense stellar environments. They always trail towards one, clearly different than what we see in the data. And it's not disputed. All multiple groups that do dense stellar environment formation, they find trailing towards one. So if you now look at the 10 solar mass region and the mass ratio, and then it's a little bit more subtle and needs more explanation in the spin, then it's clear that clusters cannot do it. And then you go to isolated binary evolution, and lo and behold, there's a peak at 0.5, 0.7 for many models. There are models that give you a peak somewhere else, but for many models, you get that peak that you see in the data. And you get the 10 solar mass peak. Breathing. If you knew for how many years we have had hypothesis, and nothing to constrain the hypothesis, this is so satisfying. That's the 10 solar mass peak. Something similar is happening with the 30 to 45 bump. It's not a sharp peak. And look at the difference. For those black holes, for that region, for the higher mass black holes, the mass ratio distribution changes. It's railing towards one. Again, the dashed lines, for those who understand the statistics, are the priors. Clear measurement. There's no peak like the low mass black holes at low values. It's trailing towards one. Therefore, it cannot be explained by isolated binary evolution, but it's consistent with stellar clusters. So not all black holes we're observing are formed the same way. Different mass regimes are formed through different channels. And we need this combination of information between masses, mass ratios, and the spin plays a role. It's a little more subtle to start drawing conclusions. We're doing real astronomy. So low masses, clusters cannot do it. High masses, clusters can do it. So a coherent picture is emerging. This slide just says what I told you already. Okay? So that is where the field is in terms of population analysis for binary black holes. There is other science about our neutron stars, testing of GR, whether general relativity is correct or not. So far, it passes every test. If it didn't pass any test, you would have known. It would be in every science magazine and science section of a newspaper, maybe even front covers of newspapers. But since the topic of this series is black holes, I focused on black holes. Now, am I allowed to take 5 more minutes to highlight something? In my introduction, it was mentioned that I'm director of an astronomy AI institute that is funded partly by the Simons Foundation. Some of the work I am research-wise, other than doing administration, that I'm involved in, has to do with how to use AI to improve the fidelity and the speed of the simulations of how stars evolve and form compact objects and other types of things. So I'll just show you a teaser, okay? So I'm gonna, here's sky, we do a lot of things. We study astronomy from stars and compact objects, which is my area, all the way to the early universe. And in terms of AI, we're focusing on innovation in generative AI, but with physics-informed constraints, and we're trying to quantify the uncertainties of the predictions from AI. We put these together in 3 pillars, and we have problems related to data in astronomy, simulations, because that's how we interpret data, as I just showed you, and also instrument design. I work in this pillar, in the simulations. And major part of my simulation work is simulating stars. And I won't go into the details, but stars, basically, a lot of physics is going on inside the stars. And we want to understand their properties inside and their macroscopic properties, because at the end, it's going to allow us to compare to all kinds of observations from electromagnetic astronomy, but also from gravitational wave astronomy. A typical code, the best codes right now that allows us to do these kinds of simulations for one star can take anywhere between hours to days for one star. With our newest AI work in about a year at this new institute, in close collaboration with experts, computer scientists, not just the astronomers doing their thing, we have now methods that are producing properties inside the stars that when you compare them to the traditional code, it gives you curves. I won't describe all the panels, but it gives you curves. You cannot tell the difference between prediction of AI and traditional computation. Okay? There's actually 2 curves here. The real, which is traditional modeling, and predicted means AI prediction. That's one example. Another example is that was one type of star, but we can do the same thing for the interior of stars across different types of stars. And again, the errors are much less than 1% between AI and traditional modeling. And for the people who know something about stellar astrophysics, here's an HR diagram. This is now not just the interior of the star. This is time evolution from birth to death when we get the black holes. And again, each curve here is a different stellar mass. And the black dashed line is the traditional solver of the equations. And the color is the AI. And basically, I got this plot today with our new algorithms and optimization. It's not perfect up there. We need to optimize a few things. But the fact that we can follow the evolution and catch all these loops that stars actually do in temperature and brightness, I mean, this is like a dream, because instead of doing these simulations in hours to days, our AI solver does it in about 1 second. So these tools are remarkable. They carry the physics fidelity we need. We have uncertainty quantification wrapped connected to that, and we can't wait to do the actual astrophysics in the coming years. I'm going to come back to gravitational wave detectors. We have a vision for what comes after LIGO, both in Europe, Einstein Telescope, and in the US, Cosmic Explorer. We'll need a decade or two. But if we can get Cosmic Explorer by 2040, I hope you stick around. I'll do my best to stick around. We'll be looking at almost 1 million black line binary black holes. We're at 200 now, and we're already drawing conclusions. I'll end by thanking my current group. Over the years, dozens of young, talented people have contributed and worked with me, and I have had the pleasure of training. And I'll end by welcoming you to the new era of gravitational wave astrophysics. Thank you. Happy to take questions.
We have time for a few questions. Be sure to use the seat mic in the back of your seats. Yes?
You showed us a graph for the first 220 detections of gravitational waves, if I read it correctly. On the vertical axis, you had the mass, but I'm not sure what you had on the horizontal axis.
Yeah, okay.
And why do we have this symmetry on the horizontal axis?
I am afraid that x-axis is insignificant. So I'll come back to that. There's no numbers and no units and no symbol. So what we're doing here is we're showing just the masses, no other properties. And then in this particular incarnation, we're telling it's an automated system of plotting. And we're just saying, put the most massive black hole mass, the most massive black hole at the center of the graph, and make everything else symmetric. And then the code figures out how to lay them out. So there is no significance. We just want to lay out the sources. But there is an actual web portal that any of you can reach. If you Google masses graveyard Northwestern, you'll find you can play with it. And you can ask for it to give you in chronological order. So which was detected first, and it will order them in chronological order, or in decreasing mass, or increasing mass. And you get different shapes. And I use this symmetric shape. It looks like a butterfly. I like it.
Thanks for the nice talk. I was wondering about this conclusion about 10 solar mass peak and 30 solar mass peak. And let's say about 30 solar mass peak, not knowing much about dynamical interaction, won't you expect the mass ratio to be more uniform? Like, because they are just keep finding each other.
Closer to 1, yeah. So there is a physical reason for that we understand. So when you put objects of different masses in a small volume, the whole collection acts as a macroscopic physical object and experiences self-gravity. And the heavy stuff sink in the center. It's called the Spitzer instability. The heaviest stuff in the center, less heavy a little further out, less heavy, less heavy. They stratify in a way. The collisions that lead to pairs of black holes, they happen at the highest density regions, so closer to the center. So the heaviest stuff is in the center. So the black holes have similar masses where the binaries form. So you tend to form binaries with mass ratios close to unity.
Yeah. As Hector will take the next question, I will just want to say that is number of 50 or 100 enough to make this statistical conclusion?
Is the number, I'm sorry,
So
of?
like we have 220 events, and do we have enough numbers to say that statistically we can say this is dynamical and this is isolated?
I mean, this is what it shows here. Statistically, it's not, it's not perfect. As you saw, the error bars of the data still have, big. We would like the data to be more like a line instead of big histograms, but it is statistically significant already now. It will only get better.
Other questions?
Can you say something about how you train the neural nets? Is it on direct numerical simulations? How many?
Yeah. Well, there's a lot of, yes. So first of all, we do train them on actual simulations with the stellar structure and evolution code that solves the equations. It's a system of 4 differential equations with another 4 constraints and boundary conditions on a grid. And we have hundreds of thousands of simulations that we have done over the years, because before we started using neural networks, we were building grids and we were doing multidimensional interpolation to be able to do Monte Carlo population modeling, and we would interpolate. So we have a huge library of real data, simulation data. So that's one thing. The second, in terms of the basic algorithm, I don't know if the words will mean something to you, but we're using physics-informed neural networks and physics-informed neural operators. Now, if you take them off the shelf, they're not working. Okay, so there is a lot of optimization, how you treat the boundary conditions in the loss function. We are doing convergence tests to make sure that, and I should say, initially we train with the data and the equations and the boundary conditions in the loss function, and then we remove the data, and we're just solving, we minimize the loss function just with equations and boundary conditions. And we are looking not just that it follows gradient descent, but it actually approaches 0, and it approaches 0 as we increase the epochs of the network, et cetera. So we're doing convergence studies. The neural network learns to do it you have to retrain it for every different boundary condition. The neural operator learns to do the whole family of solutions. So now you change the boundary conditions, which is, let's say, the mass of the star, the initial mass of the star, and you don't have to retrain it. Is that enough?
Thank you for the fascinating talk. Could LIGO detect any wormholes?
Yeah, not really. I mean, maybe I shouldn't be that fast. Let me think. Yeah, no, so wormholes, you know, you don't have the event horizon. It's not clear so the way we find the signals is through match filtering. What does this mean? Is we have a knowledge for how black holes should inspiral and merge and die after the merger through GR, and we use those predictions to cross-correlate with our data and find it in the noise. It's not clear we can do the same with wormholes. And if we don't have a template to use and search for that kind of signal in our data, we can't find anything, at least not now.